So Dave is basically an institution when it comes to computational statistics and uncertainty quantification. I know him actually, even though I'm a little bit older than him, I practically know him since the days I moved to the area of UQ, which was many years ago.
A while ago.
So Dave has been a faculty at Duke that in many ways started this revolution in computational statistics and Bayesian inference, the old good days. He moved to Los Alamos, where he was a leader in the area of UQ for many years. And recently he made an extreme step to come back to academia. And he joined, with some special agreement, Virginia Tech out of Washington, D.C. on a center called, tell me, what is it called?
Social Decisions Analytics Laboratory.
All right, so that's something like that. And,
wow, yeah.
So hopefully no social decisions today.
Yeah, you'll see how well I do socially anyway.
Okay, all right. So with that, thanks for coming.
All right, Nicholas, thanks. Thanks everyone for coming here. So as I'm blabbing away, feel free to try to get my attention, ask questions anytime. That will be just fine. Like Nicholas said, most of my life has been on looking at ways to combine observations or experiments with big computational models in the physical arena. And this talk will focus mostly on that. And more recently, I've tried to do this in the social settings. And I think I've got more gray hair now to show for that. So there's challenges, there's different sorts of challenges there that are fun and certain problems are doable, other ones aren't. But I was going to talk about a problem that kind of came up a while back when we were on this committee for V&V and UQ that the National Academies had organized. And one of the things that we tried to come up with were what were research areas in this UQ area and what are kind of domains that need understanding and kicking around. And one of them that we came up with was this idea of how do you quantify uncertainties in areas where you're really extrapolating, where you're going away from the experience of your data. So when you make computational models, almost always you want to use those to say something away from where you have data into some new setting. And we can put uncertainties on that, but how do you know how to trust these things? And at the end of this talk, you'll see I don't have any great answers to that, but maybe a few ways to maybe think about that. So part of the reason for this slide is we made up this example to try to convey this idea of how does UQ work to managers. And so what I'm going to torture you with for this next few minutes is this ball drop example. And so we made this example just to convey sort of the basic reasons about why you have to worry about computational modeling, why experimental data is helpful, and why you have difficult choices about what should you do to try to improve your uncertainties or your quality of these predictions. So this is from my Los Alamos days, and so we had test bands and things like that. So you couldn't necessarily do experiments that you might want to for the predictions that you wanted to make. But you could combine historical experiments and other types of experiments to go and do this. And so this sort of motivated this example. But here's the idea. I'm going to go pointerless, but if you've got one, it'll be okay. But if not, no problem. But
there is one. There is one.
Out here somewhere?
It's over there. Can you see it?
Uh-huh.
Yeah.
Yeah, it's not shaped the way I would have guessed. All right, so the notion is we've got this tower, and what do we want to do? We want to predict how long does it take this bowling ball to fall from different floors on this tower. And so we could go to the 10-meter floor and the 20-meter, 30, all the way up to 60. So the question is, well, how long does it take for that thing to fall? What we have is a large-scale computational model. It needs to run on HPC resources, fastest supercomputers around, right? So maybe it's not really that hard of a computational model. So F equals MA is basically our model here. But it conveys the idea. And so what we can do is we can do some experiments. So we drop it once at 10 meters and we get a drop time of something like 1.5 seconds. We drop it at 20 meters, we get a drop time of around 2 seconds. and on and on. And the tradition of those days in V&V and UQ was to hold back sort of your most difficult prediction and use that as your validation test. And so there was this nice language of, well, once you've passed the validation test, your model is validated, and you can basically use your model instead of having to collect more data from experiments. So we were trying to disabuse them of this notion. So the idea here is that, okay, we'll use these drops from the first to the fifth floors here, and what we want to do is predict what's going to happen at 60 meters, so that's the top here. And so we got a computational model, and we want to convey this idea that most models are going to have parameters in it that you need to figure out what's the right setting for these things. So calibrate these model parameters. So here we just got one, the acceleration due to gravity. Initially, we might have a fair bit of uncertainty. So we'll say maybe it's somewhere between 8 and 12 meters per second squared. So we don't know exactly what g is. And if we run our computational model over this range of different values of g, we get the spread that these white lines, these light gray lines give us. Then we said, well, why do we have experimental data? Well, they help us constrain uncertainties about these parameters. So we can go ahead and do Bayesian updating, for instance. Go from this prior distribution for g to this posterior distribution, and go ahead and propagate it through that model, and we get this thick gray line for uncertainty now. So this conveys the idea that as you get more experiments or data, you often can reduce the uncertainty of your predictions this way. So data helps you in that respect. But then we want to say, okay, well, if we use this model, we can go ahead and make this prediction at 60 meters, right? We can kind of zoom in here, and here's our prediction. We expect about 3.5 seconds, give or take. And then we go ahead and look at the validation test, and sure enough, the black dot comes in right at about 3.5 seconds. We're feeling good about this model, but we wanted to caution people that, oh, it's not necessarily validated. What happens is now you want to use this model in some new setting, and the question is, how do you know how to trust this thing or not? So one new setting might be that, oh, we have a test ban of making towers beyond 60 meters tall. And so one question might be, well, I just want to extrapolate to the 10th floor. So I would just want to extrapolate to 100 meters. So I can go ahead and make a prediction here. I passed the validation test, and what do we say about this prediction uncertainty? Hard to say, but this was the idea. So now the idea that, what could you throw money at? I'll get to this in a second. But the idea is now we have this kind of toy problem we can set up and ask questions about resources. How do we want to try to address this question, or do we come up with even trickier questions after that? I'm not going to talk much about methodology, so this one slide is the only methodology slide. And I recommend you ignore any of these equations. But the idea is that the computational model for how long it takes for that ball to drop needs an input parameter for g. So I need an input for g. Maybe I need an input for the drop height I'm dropping it from. So we have to describe the experiment, and we have to put in the parameters. And the idea is that these green dots just give me the computational model output. So the other point that we wanted to convey about here is that these large-scale computational models usually take a long time to run. And so we're not going to be able to fill up this space completely with model runs. We're going to have to guess what the model is going to say at places we just couldn't afford to run it. So there's this notion of using a response surface to try to fill in what the model would have said at places we couldn't afford to run it. Sometimes that gives us uncertainty. And then you can go ahead and fold that into some sort of inference procedure. Here it's a Bayesian case to come up with, given the prior uncertainty on G and the fact that we're interpolating or using a response surface for this computational model, we can fill that all in with the experimental data and come and make predictions. So that's about all I'm going to say about methodology, but all the examples I'll talk about use something about like this. And so if you're into more statistical details, a Gaussian process is used here. Bayesian inference is used to go from the prior to the posterior. And then we might be a little more thoughtful about error models. Well, what's the uncertainty on the observational data? Usually it's measured with some sort of uncertainty. But as we connect that to reality, we might want to say, well, here's what the model says. How does the model relate to reality? So we might want a second error term that talks about that. I'll certainly get to that in a second. All right, so we have our nice pristine model set up. We got bowling balls. Another thing that happens in the Department of Energy is that the bowling balls we used back in the 50s, they don't make them anymore. In fact, nobody makes that thing anymore, and you got to fabricate some new ball. And so maybe we go ahead and fabricate a new ball, and then we want to get some more test data from this ball. And it turns out that here's the predictions from our well-calibrated model from the 1950s ball. And when we look at this new one that we made, it's systematically off, right? And so for something like a bowling ball versus a basketball, you know what the problem is. We've got some just air friction. We got drag due to the fact that this thing is falling through air. And this thing has less density, so it's going to fall, in less quickly than the bowling ball is. So we have slightly higher drop times. And it means we have this systematic error between what the model says and what reality is giving us. So this sort of thing happens a lot. And now the question is, what do we do? And this is another thing to put out. Do we spend money on a better model? So that's one of the things we'll try doing. So instead of that old model, right, we can spend a few years of development time, come up with new physical modules, and come up with a new model, something that accounts for friction due to air. Also, when we come up with this new model, it's worth pointing out that this new model has two features in it. It has this thing that kind of felt like a physical law, right? F equals ma. Don't mess with that. That's true. And then it has this second thing that is physically motivated, but it's not really a physical law, right? It's a phenomenological component of the model. Almost any models that we look at have these two different components in it. What's hard about these phenomenological components is often that there's parameters in here, like this coefficient of drag, that we'd like to say, oh, we just want to find the right value of that and our model will work well. But what happens is phenomenological models tend to need different values for that coefficient for different types of experiments. And so it's usually less universal. So this is a problem that we tend to get with that. So let me point out that you have some things that are laws and things that are phenomenological. So that's important. The other thing about looking at a new model is it tells us something about the space that these experiments live in, right? So this model is telling us that this coefficient of drag is part of this term, but also the radius of the ball and the density of the ball are also a big deal all of a sudden. So before we didn't even consider that, but now that we think and we dig into the physics a little more, we got a more complicated setup. So we've got radius and density here to describe the experimental space. And so here's basketball. Yeah, it's a lot denser, a lot less dense than the bowling ball was. And so now we can talk about experiments in this new space. So having a better model, or not even necessarily having it, but just thinking about this better model lets us think a little differently about how representative these different types of experiments are for the prediction we want to make. So now if we ask a question, say something like this, okay, well now if our extrapolation question is about the softball, how long does it take the softball to fall 100 meters, given that we have data from the basketball, the bowling ball, and the baseball? We can try to address that question. That's what's going on here. So here's calibrating one single value of the parameter, coefficient of drag, as well as G. So here's the joint posterior distribution. That blue dot gives you a 95% region there. And then we can propagate that through the model. And so this skinny gray region gives us our prediction uncertainty for the softball as a function of drop time, or as a function of drop height. All right, so the question is, do we trust that, or what's our argument for trusting that or not? And you know, if we look at it one way, we think, okay, the radius, we have the radius here, and softball is kind of in the middle of these three balls, right? And we also have density, of which softball kind of lives in the middle as well. So you might feel better about this prediction because it's something that looks interpolative, at least in this space. And then there's other questions that I won't get into too much, but other big questions that come up with here, like if you wanted to decrease your uncertainty, what do you do next? Should we do some drops with the tennis ball or the light bowling ball? Should we do more experiments? Should we improve our computational model? Should we get better estimates of what coefficient of drag is, maybe by ball? So in terms of how, or do we want to alter our experimental facility? Can we pay a lot of money and have it go up to 7 floors instead of 6? But there's this question of resource allocation that's important. And quantifying uncertainties is one of the key ways you go ahead and figure out trade-offs between different actions you might take. All right, so there it was for, there it is for this sort of this example that we use for managers trying to convey this idea about why this problem was actually kind of complicated. And so it invited these ideas about extrapolation that we kind of took off and ran with. And also I want to talk a little bit about connecting this model to reality, that we might say, okay, reality is just this model plus some observational error. What often happens is we have a setting like this, is that, oh, we have this great model that we really would like to use, but we can't afford to build it just yet. And so we're stuck with this current model, and what we want to do is alter it some way so that we can make predictions that we might trust, given our current level of technology, and ask, well, okay, we'll hold ourselves off with that for now until we can build the better model. And so how might you connect the physical observation to the model? And some of the ways that we look at is to say, oh, we might add a term that's this systematic discrepancy between what the computational model says and what our actual observation is. So in addition to this observational error, we might model some systematic term in here. And so just as an example, we just said, one example you could use here is, say, if we're stuck with this F equals MA model for now, we could go ahead and say, okay, well, we're going to model this discrepancy in the drop time as a function of some constant times the drop height. And that constant is going to depend on what are the initial conditions of the experiment. And so here's just an idea that here's that constant as a function of the density of the ball and the radius of the ball. So here's an estimate of that from the data you've got. And then you end up with a prediction for the softball that at least might have some acknowledgement of the fact that you're doing things that you shouldn't trust your model to do, and it gives your model a little extra extendability. So there was just one example of trying to put in an extra error term or component of the model that'll help make the model be something that you want to link to reality. You tend to pay a price whenever you do that. If you do something very phenomenological, like a statistical model here, you end up with wider uncertainties for your prediction typically, and then also what happens is you end up with a lot less information about that physical parameter you were after. This is almost always the price that you pay when you go ahead and do something like this. So if we were really interested in the effects of gravity, this may not be the strategy that we want to take. If you're interested in estimating how long it took the softball to drop, this might be a good way to go. So it depends on what you're after as well. And then traditionally, just in UQ these days, there's a fair number of ways to go with how do you connect your model to reality. So one is this denial approach, right? Just to say model is reality and just be done with it. You can at least do something and say there's observational errors on top. So here's sort of the most basic thing you could start with. You could add components to your model, and we'll see examples of this in just a second. That will help kind of shore up the difference between your F equals MA model and the model you think is really going on. So add something phenomenological within your computational model. And then, like I talked about, you could do something statistical and just say, well, for now, we're going to have an error term that we're going to try to estimate, combining the data with the actual computational model. How you do this is going to be an art that depends on the actual situation you're in. So traditionally, people might use a Gaussian process, something for this error term. You might also just have an error that says, oh, the variance of this error is a function of the inputs in some ways that you want to use. So there's lots of ways to go. What I thought I would do for this talk is just talk about a couple different examples that would be kind of fun. So I don't know if there's going to be a lot of insight, but here's experience with extrapolative predictions that we've had that you guys can just have a look at and see and laugh at how I did. So the first one, and when I say I, right, it's me and a whole mess of other people. One is looking at this crash center at University of Michigan that was doing radiative shock experiments. So we'll look at that, and the extrapolation was from looking at circular tubes and this radiative shock going down this tube to an elliptical one. All right, doesn't sound that bad. We'll see how we do. Another one is on binding energies. So this is for nuclei. So we look at atomic nuclei and start looking at how stable are nuclei as you start adding neutrons to it, and do these models predict well given they've trained on stable nuclei. And then the other thing I'll talk about is this ball dropping example. So it has fun videos, but we were so successful with using this ball dropping language to kind of convey these ideas to managers and funders, and the idea about what are the issues for UQ, that we were able to talk these people at the Nevada test site into dropping a ball a good 1,000 feet down, and we tried to predict how fast those things would land. So I'll talk about that one at the end. All right, so here are some simulations of radiative shock experiments. So what you're seeing is just a shock moving down the shock tube. And all we're really going to track for this example is just the front of this shock. So just track the front. And so it turns out, depending on what you do to your simulation, you're going to have that front move at different speeds. And what does it depend on? Well, what happens is a laser hits a beryllium disk, and that disk basically explodes, and it moves a shock down the shock tube. And so the energy of the laser is a big factor going into that. The thickness of that beryllium disk is a factor that affects the shock. The diameter of the tube is going to be a big deal. The gas pressure in the tube is another one. And then this last parameter, energy loss, is one of these phenomenological things that you go ahead and put into your computational model. So it turns out that if you just simulate this thing, particularly in a dimension-reduced model, a 1 or a 2D model, almost always these models don't lose energy the way the real system does. So this is a known problem with a lot of these things, and a way out is to put in a term that drains energy out of your simulation as it's moving along so that it looks more like reality. So definitely one of these phenomenological modeling terms that's going to help that experiment look more like reality. All right, so lots of different simulation runs, and now you can just imagine each simulation run gives you a location and a time point. And so you could imagine each simulation we could just map as a line. Right, so for instance, this simulation is saying here's time, here's location down the shock tube, and so this line is just mapping the shock front from one of those experiments. So each one of these gray lines is a computational simulation. So it's that shock tube moving down. It depends on a number of these different parameters, right? And then what we also have are physical observations. So we have a number of experiments where we captured how far down the shock tube was at a certain time. So if you took a picture at 14 nanoseconds, then here's how far each of those different shocks were. So from a given experiment, we're going to have a number of these parameters that we're going to know for the experiment, and we're going to calibrate this energy loss parameter. All right, so most of the experiments are using these cylindrical tubes. So what you're seeing here is just a cartoon of the shock tube. So some of the these two shock tubes are going to be cylindrical. This one's wide and this one's skinny. So that's a factor that's going to affect how quickly the shock moves down that tube. And then we have this other one that just happened when they were trying to build these tubes and make an elliptical one. They had one that started out as wide and then turned skinny. So that's sort of the symbol that goes for that one. And then the extrapolative prediction is to predict this thing for a shock tube that starts out wide and then turns into something elliptical. So it gets skinny in one direction and it stays wide in the other direction. So this thing is the extrapolative one. So here's the shock tube that's elliptical that we want to predict. We're going to use these types of experiments to train it. And so mostly we're estimating that parameter of energy loss. And we're also looking at errors that we see that are systematic. So we did need to think something about what were we going to use for that error term that might be systematic. We tried two things. All right, so notionally, we've got this uncertainty due to that energy scale factor. So from all these experiments, we could estimate that thing. So this is going to go on simultaneously, but we have a posterior distribution for that unknown parameter. And so that's going to give us some prediction uncertainty for any given experiment because we don't know that parameter. We're going to wiggle it around according to that posterior. But then we're going to model some terms for the structural error so that when we make a prediction, it's going to be the parameter uncertainty propagated through the model plus some structural error term. And that's going to give us our prediction. And the structural error terms that we tried is one, we had just had a variance term that just grew as a function of time. And the other one, we used a Gaussian process that we tried to train from historical data. Are these great models? You could probably think of something better, but we had like 2 days to come up with these predictions before the experiments were going to happen. So those are the two that we kind of encoded into something very quickly. So here's an impression of trying to describe all these experiments. So here's 1, 2, 3, 4, 5 by 4. Here's about 20 experiments that we're showing here. And this last one's the extrapolation. So let me just take one here. So here's an experiment. When you run the experiment, you can see what the laser energy is because you can measure that when it hits the disk. And we also can look at the tube diameter. So we can see, oh, this is one of the skinny tubes. So this reminds me. So here's a skinny tube. Here's the laser energy. And we also know the thickness of the beryllium disk, which turned out not to be a big player here. So just these gray lines are the simulation runs that we did, uncalibrated. And then the green lines are going to give you the prediction when you use that, when you calibrate that one unknown energy loss factor parameter. And then on top of that, the black lines give you the prediction we make after we calibrated that error term on top of things. So it's basically going to give you this prediction of where do we think the experiment's going to show up. So what we did in each of these experiments is for this prediction, we trained on all 19 of the other experiments, and then we made a prediction for this one. And so we'd like it to fall within the black lines 90% of the time. And so that's what happens for all these. All these are a holdout that we're showing. So this one's kind of on the edge of that black line. One thing that we noticed very quickly was that if we looked at all these experiments we got here, almost all of them are from the skinny tube. And this just happens in these experiments that, okay, we got the skinny tubes up and going. They had some experiments happening. Then we realized, oh, we better get some fat tube experiments. And sure enough, we got some of those. And a minor problem here is once we had all those three wide tube experiments, we noticed that all the arrival times were late. So the pictures were taken kind of late to get the shock tube arrival times for these three experiments. They're all early for this one. So we're hoping like, oh, can we do some skinny tubes where you take the picture a little bit later in time and can see where that shock front is. And so these last three were those. And so now at least we feel like we got enough coverage where we feel like, okay, maybe we can go ahead and make this prediction. So before we did the actual extrapolation, what we did is we took out those special tubes, we took out the data from those ones and asked, well, how well are we going to predict those? So in some ways they're an extrapolation too, because either of the tubes would have been all skinny or all wide, but certainly cylindrical, so certainly circular on their cross section. But these ones went from wide and then they funneled down and were skinny. And so these ones were kind of special. They're slightly different. So we're asking, well, I wonder how we did on those ones. So we actually did the predictions on these ones, came out, right in the middle of our uncertainty bar. So we're feeling pretty confident going into the extrapolation experiment. So here's our prediction for the extrapolation experiment. So it has the elliptical tube. We don't know exactly when they're going to take the picture, so we don't know how far along the tube is going to be when the picture is taken. But for a given time, we've got a prediction for where we think that shock is going to arrive. All right, so how do we do on that? So I'll blow that one up so you can see. There it is. And not only did they do one experiment, which if they'd just done this one experiment, I would have felt really good about myself. But no, they did a whole mess of experiments. And so some are right in there, but some not so much. And so we have two different predictions here because one uses the Gaussian process model and one uses the linearly expanding variance model. And so they don't give two very different predictions at the end here, but all of these had a 26 nanosecond time and a fair bit of spread. So do you guys grade hard here at Notre Dame? I bet Nicholas grades pretty hard. So for me, I was like, okay, that's not so good. I'll B+. But yeah, Nicholas, what do you give me? A C-? Yeah. Oh well, I did the best I could on that. All right, so wow. So I thought, okay, extrapolation is a little bit hard. If we looked at how the model was doing, maybe there were signs that, oh, maybe it's not doing the aspect ratio change from circular to something elliptical very well. So there were maybe some thoughts about that, but I don't want to harp on that too much. Okay, so I've tried it once, C- in Nicholas's class. If I'd gone to my class, B+. All right, I'll go now we'll do another example. So this one's on the binding energy of atomic nuclei. So these are big nuclei that we're usually talking about. So if you take a nucleus, mostly neutrons and protons, about the same number jammed together, those tend to be stable when they're about the same number. If you start adding too many neutrons or too many protons, they become unstable. And one of the ways they measure stability is this binding energy. So it just says if I take a nucleus, take all the neutrons and protons and move them out to infinity, how much energy does that take to do that? And so that's what the binding energy is. And so this is kind of a crude map of binding energy as a function of the number of neutrons and the number of protons. And so what happens is, there's a real high point in the middle here, and then it gets less and less stable as you move away from this sweet spot of neutrons and protons that kind of follow this line here. So if you look at what elements do we see in the universe, right? It's only elements that kind of live along this line where things are very stable. And so at one end we've got hydrogen and helium and stuff up here. And at the other end, we've got very large nuclei like uranium. And so if you keep breaking up uranium, it goes from things out here, it breaks into pieces that start with move on to something that's even more and more stable if we look at the binding energy per nucleon. And so in the middle is stuff that's pretty stable, like iron. And so if you break big things like uranium, you'll gain energy until you get to something pretty stable. Likewise, if you take this small nuclei and put them together, you'll gain energy until you get up to something up here. So all this curve of binding energy is really important for understanding nuclear energy. Also, if we talked about binding energy and other more details of that, for understanding nuclear fission and nuclear fusion, it's important to understand these sorts of things. So this model is really crude. I think I just got it off of Wikipedia or something. The models we're working with are with nuclear density functional theory. And I don't want to talk too much about that, except that they've got a number of terms here that have to do with, say, the coulombs, pairings, distances, and then it has these chiral factors that they kind of expand out. But basically, there's a number of parameters here that describe how densely packed a nucleus ought to be, what it looks like on the edges, sorts of things like that. So we've got, I want to say, around 10 to 12 parameters that control features of the nucleus as you put it together, put more and more neutrons and protons in there. So this DFT, it really minimizes what's the binding energy. So it gives you basically an energy potential, and then when you put a bunch of neutrons and protons together, it'll solve for the minimum energy state, and that's what we think the binding energy is. So that's how these things work. So what predictions do we want to make? Well, what you see here, this gray line, is just all the stable elements that we know about. And what we have for these black dots are training data. Same thing for the green dots as well. Those are also training data. So the black dots are special training data. These things are spherical nuclei. So they're nuclei that the model has a hard time with. But they're important because they have these really special features about how the stability of nuclei. And then these green ones are, they call them deformed nuclei, but the model does a fair bit better with those ones. So we have training data, the black and green dots, and what we want to do is predict the stability of these neutron-rich nuclei that are going to be made at these experiments at Argonne National Lab. So they already did the experiments, so we trained on this data. We wanted to make predictions for what the binding energies would be for some of these nuclei out here. And then it's just a neat thing about stability of nuclei. There's sort of this open question about whether or not there's a super large nuclei that have never been put together but might still be stable. So if you remember back in the like World War II days in the Manhattan Project, plutonium was one of these things that had never been made until they made these things in the reactors. And so there's questions about whether or not there might be a stable super heavy nuclei out there at very high N and Z numbers. So far no one's found them, but and no one really trusts these models for that extrapolation. But they think maybe it'll work all right for this kind of extrapolation. So what we do is we end up training that DFT model with about 10 different parameters. We also look at how well it matches the data that we do have in order to make predictions in this new setting. And so, yeah, we won't spend too much time on this, but basically for any set of neutrons and protons, I and J is indexing that, we'll have a experimental binding energy, which is basically measured almost exactly. There's effectively no experimental error. We're going to say that's going to be the model prediction plus this misfit term. And this misfit term we're modeling as just a function of the number of neutrons and number of protons. So it's not a very sophisticated model, but our hope is that by seeing how well it fits the data we do have, we're going to take that uncertainty and map it into the predictions that we are going to make. So really we're going to rely on that model to do about everything for us.
So when you're calculating the misfit function, is that, do you put any physical insights into it too? Or just
Yeah, so on this example we didn't, but the current work that we're doing with these guys, yes, we're trying to do that. How much can you do? Like, okay, the sort of the real basic version is just say, oh, it's a function of the number of neutrons and number of protons. And in fact, if we go back to this picture, We know that there's a lot of similarities as you just start adding neutrons to a nucleus, so that if we're seeing we're systematically low for this one, we're probably systematically low for anything along this line. So something as unexciting as that is one thing you could do. Can we get inside this DFT functional and try to do something better than that? That's what we're kind of looking at, because we have ideas about what the next term in this DFT series is going to be. So can we use that to help us build a smarter misfit function? That's what we're kind of looking at now. So far, lots of potential, not much success is where we are so far. That's a good question. So no, this one is actually going to be kind of boring for this example. So what we're going to do is do simulations at each one of these data points, and also simulations at these places we want to extrapolate to. Oh, and I did have to, I had to argue with a program manager once that he thought, oh, you have Z's that are below that and above that. You've got N's, number of neutrons that are above and below that. But that thing's not an extrapolation at all. So I had to say, oh no, I think it is. Like, here's where we have our data. It's definitely away from that. So I think there's even some argument about whether or not this thing's an extrapolation. But one of the things that's hard about this, or one of the reasons it's going to be hard, is that you're going to go off this edge of stability here, that as you try to get nuclei that you add more and more neutrons to, pretty soon it's going to be very unstable and a hard thing to capture. So the physical system is changing quite a bit as you're adding neutrons to these sorts of things. All right, so how does that work? All right, so here's a quick explanation, and I'm really just going to let's just focus on these on these simulations right here. So every green line is a simulation. What you're doing is you're putting in different parameters. So if you zoom in a lot, you can see that there's about 200 different simulations. So there's 200 lines here. It's not just one green line. There's 200 little hatches going across. And where that black line is where the observation is. So we ran 200 different DFT simulations. They're varying because we use different parameter settings. And then what we'd like to do is find a parameter setting that seems to capture the observations. So here they are for these spherical nuclei. Here they are for these a bunch of deformed nuclei, the green dots. And then for the spherical ones, we can also measure things like their radius. And certain ones seem like they might be kind of hard to figure out. And then here are the simulations we have for those extrapolations we want to make. So those are the radii that are out there in the high neutron area. So I'm just going to take this set of simulations, zoom in. Oh, no, I didn't zoom in. What I did is I centered at the middle simulation. So I have 200 simulations. I just take the average and center there. And so now I can make this picture, so it's the same picture. It's just centered at the mean of the simulations. And you can see that, it seems to predict the mass pretty well for the symmetric radii, or the spherical radii, but it doesn't predict the radii very well. All right, and then I'll zoom in from that, and then you can see even the ones that looks like it's predicting really well, it's not, the very center of the prediction isn't fitting all the data very well. So the calibration is finding parameter settings that seems to match the data. So that's what we're going after. Here are sort of the intermediate plots we made on the parameter calibration. So here are, 12 different parameters here. So what we have initially was this 12-dimensional space that was a big 12-dimensional hypercube where the uncertainty was. And then conditional on all this data, it shrinks down to something that's this 12-dimensional blob. And so what you're seeing here on the diagonal is just the one-dimensional margins of that 12-dimensional blob. And on the off diagonal, you're just seeing two-dimensional things. And the red dot was sort of their old value that they used the last time they did something like this for these parameters. And so we're not getting exactly the same answer with this approach. Because we're using a slightly different error model here is one of the reasons. And it's also a new DFT model they've got. So in the end, what we could do is we could propagate that parameter uncertainty along with that misfit uncertainty to make the predictions for these neutron-rich measurements that are going to happen. So these blue regions are the uncertainties that we predict from the model and this whole formulation here. So those are 90% prediction intervals. I think I'll zoom in a little bit. So I'll center and zoom in. And then I'm just showing the same things, but the blue part is the uncertainty due to the parameter, due to the fact that we don't know the parameters exactly. And then the light blue is due to the fact that we have this misfit term. And so what we learned on the misfit was the misfit is a lot higher for the spherical nuclei than it is for the deformed ones. And so most of these predictions are for deformed nuclei, so all these nuclei are deformed ones. But the first 4 are spherical, so they're going to be much harder predictions, and we think we're not going to be as accurate for that. All right, Nicholas, you ready to grade? So here's where the experiments came in. So most of them are right in there, and maybe it's too good. What do you think? All right, I'll give you I'll just let you know where I stand. I would give myself an A. Good job, Dave. What do you think? Yeah, okay. All right, if I'm going to complain about anything, I have 90% intervals here, and I would have expected to get 10% of them on the top 10th or something like that. So I don't see as much variation as I would have guessed. That said, these aren't really independent predictions, right? You see, we did these predictions that were adding neutrons, so a lot of these nuclei just have more neutrons added to them. So they're not necessarily independent, so we wouldn't necessarily expect that, but those ones seem to go okay. All right, so are there lessons to say for extrapolation? So here's kind of the lesson slide, or one of the slides of lessons here. Yeah, sometimes it seems to work and sometimes it doesn't. So it's hard sometimes. What we learned from the ball drop was that if we think about it and get a model, we've got a space, or we can come up with a space of how things are in extrapolation. And so here, if the radius and density are different, we think, oh, it might be extrapolative if we just go far away from those two things. But if we thought harder about this system, we've thought about, oh, the softball, or the basketball, how is that different from the bowling ball? It's different more than just in radius and density. It's different in probably 100 different ways. And so in order for this prediction to work well, really those 100 minus 2, those 98 different ways that those things aren't the same, that has to not matter in making this prediction. And so that's the thing that you have to convince yourself of, that I've captured the important features that this system is really depending on. And if you don't have that, then it's harder to say, have you gotten them all? So I went back to the statistical literature and asked, well, do we ever come up with ideas of figuring out which dimensions are the most important ones? And if you go to what is statistics, can we point to some advances in statistics in the last decade or two? And one of them is these sparse regression solutions, things like lasso or compressive sensing, lots of Bayesian versions and model selection. What do those things do? So here's statistical regression sitting over here, right? Y equals f of x plus some epsilon, and you want to estimate this function f of x. What all these methods do is say, well, if you have a really wide x vector, or make a model that's going to figure out which of the few x's are really active here, figure out which ones those are, and then basically make a regression model that only uses these active ones, these 4 active x's, not all 500 of them. So this model selection being built into things like lasso or Bayesian model selection has really made us think that, oh, we can solve these problems by figuring out which dimensions are important. And then all of a sudden we have a regression model for these predictions that do really well. So yes, we do that a lot in statistics or in compressive sensing and computer science. But what do you need to do this? You need a lot of data to do that. So in places where you have a lot of data, you might be able to figure out what are the important dimensions, and then ask yourself, is your next prediction going to be an extrapolation relative to those important ones? So there's this idea about that, but that's great if you have a lot of data. Most of these settings where you do big computational models, you do those exactly because you don't have a lot of data. It's hard to get. So this is going to make it hard to use this idea for extrapolation. And then the other notion that was just interesting to think about was also in the machine learning literature. One of the big breakthroughs was just this basic idea to say, if we got a big training set, let's take half of it and just use it as a validation set and just see if our method works real well. So what was really good about that is that now you didn't need a PhD in statistics to come up with a new model. You can do all sorts of things, come up with all sorts of wild models. And if it does well on the holdout set, it's a sign that your model is a good idea. And a lot of these big CNN sorts of models they figured out these were good by just trying them out in this sort of way. But the notion of taking this, your whole data set and splitting it into test and test or training set and then test or validation set, if you do that randomly, it's saying, well, I'm going to take extrapolation totally out of the equation, right? Because if you do it randomly, then all these ones are statistically just like the ones you're training on. So your holdout and your test set have a lot of similarities. Whereas had you held out things that were different in key ways, held those out of your training set, then it might say something a little more meaningful about your extrapolation error. So I have this notion of maybe the way we do holdouts, we might be able to do holdouts in different ways that might help us more with assessing extrapolation error. All right, so there's that. We're not going to go there, but we'll go back to the ball drop, though. So since the ball drop kind of took on a life of its own, we knew we were going to go down to the Nevada test site, and they were actually going to try to measure how long it would take a ball to drop 1,000 feet from the very top of Nevada down to this tunnels where they do a lot of these underground experiments in Nevada for the Department of Energy. So it's not just like, oh, here's this weird idea, let's just go do that there. The Department of Energy, like at the test site, they have to keep their engineers trained and ready to do experiments, because what they do is a few high stakes experiments every year, but that's about it. And so what they really need to do is get all their people in shape and ready to do those things so that they can pull them off without making any sort of crucial errors in terms of setup. And so what they do with a lot of their younger engineers is they get them to do different sorts of things to stay in shape over the course of the year so that they'll be ready for these big high stakes experiments. And so one of these training exercises was to time how long it would take a ball to fall 1,000 feet down to the bottom of this Nevada test site. So before we did that, I invited some people out to this workshop here, and then we did that. But we tried a bunch of test drops of the ball over at different heights, different types of balls. And of course, the engineers complained about how bad our timing system was here. So it's just a video, and you can get a sense of how far that thing has dropped. But the idea is we did a number of different balls. We did bowling balls, basketballs, softballs. The bowling balls were kind of a destructive test. It was hard to use them again after that. So we had a number of test cases, and then we all made predictions for how long would it take a bowling ball to fall at the Nevada test site. First, they tried the basketball, right? So in fact, this very basketball was the first one they tried, and that one, I'll tell you about that one in a second. So here's there's the bowling ball falling. And it falls somewhere between 7 and like 15 seconds, right? It's still falling. So yeah, what happened with that thing? So we had cameras, right? So part of the thing is to set up cameras and do all these sorts of things so we can see what's happening with that. Oh yeah. I should have saw that coming, right? I figured out the basketball, that would have happened with it. So with the basketball, in fact, it moved so much, it went down some side shaft, and it's probably still there today. So yeah, the drop time for that one's infinite, but this one happened. Also, other things that happened, which I think are good for their training, right? You can look at this one. Equipment's going to break, and you need to replace it and do these sorts of things, and so they're happy that their engineers have to be trained to take equipment and if it quits working, right, replace it and things like that. So it's probably a good training exercise. And then finally, we have a couple drops that seem to have gone cleanly through. So here's one. So if you look real closely, you can see that ball kind of fall down there pretty fast. And then, then they had the high-speed cameras at the end, so we have this great landing shot of that thing splashing down. And so to do the timing, they set up a number of lasers going across here so to get a very accurate timing. So we have the time up to 6 decimal points in seconds and things like that. So the question is, how did that work out? So we all made predictions, uncertainties for how long it would take that bowling ball to fall. Oh, and so these bowling balls would kind of break, right? A lot of them didn't make it. So this happens a lot at the test site. They do things like this. So they have this crack team of people that will go to various pawn shops in Las Vegas And they can find all sorts of things. So they got us lots of extra bowling balls so that we get a few that would make it. And yeah, so we got some clean timings for a couple of these things. And then we all had our predictions as well with uncertainty bounds across it. And well, a few of us did the predictions. Most of us were it was too much effort to try to figure out how do you do that. But yeah, so I had the prediction uncertainty bounds, whereas my lower bound was certainly, all right, that's kind of low. No ways of going that far. But the drop time they gave us was definitely lower than anyone's lower bound for their prediction uncertainty. And if I made the calculation, it was definitely lower than the drop time would have been had there been a vacuum rather than any air at all. So an open question sitting around here for this is a downdraft? Is there enough downdraft to explain that or not? And I haven't summoned the energy to try to figure that one out. But we all didn't do so well on prediction here. So there's a great quote from allegedly from Niels Bohr that prediction is hard, especially about the future. So yeah, extrapolation is hard, but I think there's ways and principles to go ahead and work on this with. So I'll end it there. We talked about different ways you connect models to reality and things like that. And my experience has been it's been tougher than I would have imagined, even in this very physical setting where we felt like we trusted the models. So thanks for listening and humoring me.
So what's the relationship between the number of parameters and accuracy and uncertainty? So usually when you have more parameters, you end up having higher accuracy in some validation set. How does it affect uncertainty?
Yeah, yeah, good question. So that's a big one.
Can you repeat the question?
Oh yeah, so what's the trade? How do a number of parameters affect uncertainty for these sorts of predictions? Quite often, it's well known, quite often a large number of parameters will give you more model flexibility, so you might predict better. And of course, the test versus holdout set helps you say, how much of these parameters do you really want to use? So that helps in that setting. In the extrapolation setting, what you really want to do is keep all the parameters that you think might be important. Let those things vary, even if they're not helping the prediction very much. So a lot of parameters will trade off. For instance, accelerate just in the ball drop, the acceleration due to gravity, I can make that lower, and I could make the effect of that coefficient of drag lower and get about the same answers if I made them both high. So those would trade off against each other. And a lot of systems have this sort of property. If I don't know which one of those two things it is, I like keeping both of them in there because now I'm entertaining solutions that span this whole range. So that in the predictions I'm making, I don't see the effect of that trade-off at all. The prediction's almost always the same, but the explanation is different. It's a lot of gravity and a lot of drag, or little gravity and a little drag. And now for the extrapolation, since we're able to distinguish which one we got, we should be considering those both for the extrapolation. So there's this general principle that things that might matter, even though they're not affecting your solution much or your uncertainty much for the data you do have, they might affect it for your extrapolation. So that's different than other settings where you might want to say, oh, I'm only going to use the parameters that really seem to matter. For extrapolations, we think we want to incorporate more uncertainty parameters that may not really matter there, but they might matter in this new setting. So yeah, there's one answer to that.
Yep.
I have a quick question regarding the DFT uncertainties. So in terms of the actual experimental values you got, is there any associated uncertainty with those, your actual observations, as opposed, because I just know some fields, sometimes the simulation is considered more accurate than the actual.
Right. Okay, so the question is, in DFT, in some areas of application, people might even think the DFT code gives more accurate results than the actual experimental observations. I am told for, and I've seen it in this data, for things like masses or binding energies for these large nuclei, that they get very, very accurate answers. In fact, the data they picked were ones they thought they had very accurate answers. So compared to any DFT uncertainty or like anything you can even draw, it was effectively 0 in that case. So for the large nuclei and just the stability, well, those were measured very, very accurately. But you're right, that's not always the case in depending on the area you're looking at. In which case, yes, you'd want to put that experimental uncertainty into the analysis, meaning that you would probably have more uncertainty in the parameters since it couldn't really discern things that had to fit exactly right. So yeah, their observational certainty was 0. I'll also point out that's actually very relevant in a lot of big data settings, that quite often, given your model with tons of data, that the uncertainties you get in your prediction that are kind of from statistical estimates are basically 0. Meaning that whatever describes the uncertainty between your CNN or whatever your model is, it's not statistical, it's not uncertainty in not knowing parameters or observational error, it's misfit uncertainty. And that tends to have a lot worse properties, that you can't just keep averaging to get rid of misfit uncertainty, it sticks around the whole time. So the fact that you have to deal with that in big data problems is very similar to a lot of these computational modeling problems or UQ problems. That uncertainty due to the fact that you just have a bias between model and reality is a tough thing to get rid of.
So in the shock tube experiments that you were looking at, in some sense, the elliptical tube has an input parameter that you didn't have in any other way,
Yeah.
the aspect ratio.
Yeah, that's right.
How do you estimate a discrepancy term in that case?
Yeah, so that one, yeah, so that was kind of special, that the extrapolation was in a dimension that none of the experiments even explore. They were always assuming that aspect ratio was 1, and then all of a sudden you wanted to go to an experiment where that's 2. So we could simulate out there, but we couldn't get there. So, all right, so I think that's a great question, and certainly that should raise a red flag. So in hindsight, like, oh, that's an extrapolation we didn't get to explore experimentally at all. It's all model getting us there. And I think the one hope was, oh, we saw those funnels, and the thought was, well, all right, now it's shrinking down, but it's shrinking down radially symmetrically from the wide tube to the skinny one. Maybe that might have some of the features of the extrapolation. And if we ask how well do we do on that, maybe that carries over to the extrapolation. So that was the thinking. But yeah, so in a sense, that one's a hard one to build any kind of, use any sort of continuity arguments to say, oh, I'm doing well here, so I ought to do well there. I didn't even see myself doing anything at all as the tube started going from circular to more elliptical. So yeah, that's a good point. And that's one that we kind of remember now, that, oh, do we ever see any sort of creeping towards the extrapolation we're trying to make in some ways? But what happens a lot is you might see a dimension where that's happening, but there might be other dimensions where that's happening that you just didn't think of until after the fact. So that's a good one to point out, that the nature of that one was somehow different than just adding more neutrons, because we've seen a lot of masses where we had more neutrons added to the same number of protons.
So maybe your B plus was justified.
Yeah. B plus is good. I don't know what, Nicholas, you gonna cave in on that?
Not yet. Any final question? Well, Dave, thanks for coming.
Thanks for coming, everyone.